In the past, we have talked about congruent shapes and congruent polygons, which basically meant that all angles were the same measure and all sides were the same measure. In essence, you have the exact same shape. We're going to be talking about something similar, which is similar shapes and polygons. Now, there are two things required for two shapes to be similar. One, corresponding angles have to be congruent, and two, the corresponding sides have to be proportional. Here are some things you want to take note of when talking about similar polygons. A similarity statement is just like a congruent statement. You're saying which sides and which angles correspond in one shape to the next. This little tilde squiggly line here in the middle, that means similar. So this would say ABCD is similar to EFGH. Just like in congruence, the order matters. This would say that angle A is congruent to angle E, angle B is congruent to angle F, angle C is congruent to angle G, and angle D is congruent to angle H. This also says us which corresponding sides we have, and of course all of those have to be proportional, so each of those corresponding ratios can be set equal to one another. So we have AB over EF is equal to BC over FG, etc., etc. Here's an example of two similar shapes. The similarity statement here would be ABCD is similar to A prime, B prime, C prime, D prime. These lines on top just mean prime. It's just another type of variable. So we can see A is congruent to A prime, B has two congruent lines, B prime has two congruent lines, etc., etc. That's why we matched all those up in the similarity statement. Let's take a look at their side ratios and see if they're proportional. First, we've got the side AB, and we've got the side corresponding A prime, B prime. We can write that as 7 over 3.5. That should be equal to any other set of sides. Let's do BC and B prime, C prime. That would be 6 over 3. Another side would be CD and C prime, D prime. That would be 4 over 2. And our last side would be AD and A prime, D prime. That would be 8 over 4. And looking at all of these ratios, you can see that 7 over 3.5 is equal to 6 over 3, is equal to 4 over 2, is equal to 8 over 4, and all of these could simplify to 2 over 1. Alright, last up is the scale factor. And the scale factor is just the ratio of corresponding sides. Here we have triangle ABC is similar to triangle DEF. First, let's find the scale factor of triangle ABC to triangle DEF. Since triangle ABC is lifted first, we want to pick one of these side lengths first. Let's go ahead and pick AC. That's going to be a side length of 7. Now the corresponding side to AC is DF, so we'll put that over 14. And we can simplify the 7 over 14 to 1/2. So the scale factor of triangle ABC to DEF is 1/2. And you could see if we chose any of these other side ratios, like 10 over 20 or 6 over 12, that would also give us a scale factor of 1/2. Next, let's find the scale factor of triangle DEF to triangle ABC. This time we need to pick one of these side lengths first. Let's go ahead and why not do DE? It's just as good as any others. That's a side length of 20. And the corresponding side to DE is BA, so we could divide that by 10. That's going to give us a scale factor of 20 over 10, which we can simplify to 2. And if we picked any other sides, like 12 over 6 or 14 over 7, those would also give us a scale factor of 2.